Thanks, Ollie. Next up, I want to invite the editor of the ECMAScript specification and one of the members of the ChakraCore team, our JavaScript engine, Brian Turleson, to tell us more about TypeScript and Chakra. Brian? Cheers.
Thank you. Just got to get ready for my demo here. Give me a second. All right. I think that is set to project. And I can advance my slides. Excellent. Yeah, so I work on the ChakraCore engine at Microsoft. I also work on TypeScript, and then I do a bunch of JavaScript standards stuff. Kind of a language nerd, so if you want to talk to me about language stuff later, I would love that a lot. So I'm going to talk to you today about two products that I think really changed the game in terms of building phenomenal JavaScript experiences, both on the web and off the web. The first one that I'm going to tell you about is ChakraCore. ChakraCore is an open source, cross-platform, standards-compliant JavaScript engine. If you're familiar with the Project V8 from Google, that's the JavaScript engine that goes in Chrome. ChakraCore is sort of similar to V8 for Edge. It's a JavaScript engine, and it runs your JavaScript code. It kind of looks like this. If the clicker works. In the middle, you've got all of this sort of components that are necessary to run JavaScript code. It's pretty complex. And outside of that, you have some additional capabilities. So almost 2 years ago now, we open sourced ChakraCore. And we did that by basically taking the core parts of the JavaScript engine that was in Edge, which was called Chakra, hence the name ChakraCore. And we moved all of the development over onto GitHub and have been doing development in the open now for almost 2 years. And so the purple parts on this chart, those are the parts that are part of ChakraCore. The gray parts, they're really not relevant for cross-platform development or really anything other than Edge-specific stuff. So those aren't part of ChakraCore. It's just this purple stuff. So there's one thing that I want to call out here, and that is the box at the top, the JSRT hosting APIs and the modern diagnostics APIs. These are really awesome tools because they let you embed ChakraCore in your application, whether it's a native application written for the Windows Store or just your own application that you're compiling yourself. They're really simple C APIs, so they're really easy to use regardless of what language you're trying to use. There's really a lot of awesome things that you can do when you add JavaScript to your application. So for example, you could have scriptability in game, like a game, where the game logic is actually implemented in JavaScript, and you don't need to rebuild or recompile when you make changes. ChakraCore is used in Cosmos DB, which is a sort of MongoDB-like document database that runs in Azure. And there's also another really cool project that I want to talk about that uses this API, and that is Node ChakraCore. Node ChakraCore is a version, a flavor of Node, if you will, that uses the ChakraCore engine instead of V8. This is implemented by basically implementing a translation layer from the API that V8 expects to those JSRT APIs that I referenced earlier. Node ChakraCore is really cool for, I think, a lot of reasons. Additional diversity in the VM space, I think, will be really beneficial to the Node community overall. But one of the reasons why you might want to use ChakraCore in your sort of day-to-day development is a feature called time travel debugging, which lets you take a trace file of a JavaScript program, and you can debug it later and step forwards and backwards through the execution as if you were debugging it live. It's the same interface. You set a breakpoint on code, you step forward, but you can also step back. And you can step back to a previous breakpoint even. So it makes it really nice to debug really complex problems, especially if they occur in production or something like that. I use NVS, which is the Node version switcher. This makes it really easy to download Node ChakraCore if you want to experiment. You just it's just a single like command line flag, NVS add ChakraCore, and then you can switch between Node ChakraCore and vanilla Node really easily. So that's something that you might want to check out. But let's talk about how ChakraCore delivers scalable JavaScript, how ChakraCore makes your JavaScript experiences light up as best as possible on the web and in Node. And our journey starts here, the parser. This is the parser's job is to take your source code and translate it to an AST. An AST is just a tree representation of your code. It's convenient for the compiler. But already we've actually hit our first bottleneck. You can't run code until you parse it. And you have to parse a whole lot of code before you even know what you need to run. So this is a hard stage to get away from. And if you look at a bunch of top sites, a significant chunk of their time is often spent just parsing their payload. A megabyte of JavaScript could take hundreds of milliseconds on some devices to parse. So this is a really important piece of the pipeline that has to be as fast as possible. I kind of lied when I said you have to parse everything. There's a bunch of tricks that we can do to avoid work. One of those is defer parsing, where, for example, if you have a function that you don't call right away, we just will skip over it and come back to it later when we need to. And in fact, we've done a bunch of work in that space recently. We can now defer parse blocks, like the try block of a try catch. We'll just skip over that until we think that we need to go and parse it because we have to go execute code in there. There's another thing that we're doing too, which is it turns out much of the code that exists on the web is minified. And that makes a really interesting thing for us to look at because minification tools tend to produce certain patterns and have certain attributes that we can actually go and optimize against. There's sort of a misconception that minified code is often faster code. Byte for byte, it's actually slower because you're cramming more language into a smaller piece. So this optimization is really about sort of recovering some of that loss from minified code. So after the parser, we hit the bytecode compiler. This guy's job is just to translate the AST into a bytecode that is architecture agnostic, and it's just a helpful format for both the JIT and the interpreter, which I will talk about now. So after we have the bytecode, we pass it over to our execution engine. Execution engine can run two kinds of code. It can run machine code, that is designed, basically assembly code that runs directly on the platform that you're trying to run. And it also has a profiling interpreter. And so I'm going to talk about this interpreter because it's actually one of the key components of ChakraCore's architecture that enables really great scalable performance across massive JavaScript sites. So ChakraCore's profiling interpreter is it gathers profile information. So as you're running your code in the interpreter, it might not be running as fast as it could be in the JIT, but it's still doing useful work. It's gathering information about the types that are involved in your program, and it's handing those over to the JIT. So if the JIT does actually have to go and produce code, it can do a better job because the interpreter has gathered all that information up front. It also enables low latency execution, which is to say JITs take time to do work. You can think of JITting as trading off upfront investment in memory and CPU time in order to save that time later in execution. But sometimes you really don't want to spend any time up front. You just want to start executing code. And the interpreter lets us do that. As soon as we have the bytecode, we can start executing in the interpreter. And it's actually pretty fast to execute code this way. You know, I'm not talking about 1,000x decrease in performance here compared to the JIT, or even 100x. It's usually something like 10x. It depends drastically on the kind of code that you're running. But there are actually a lot of scenarios where interpreter performance is just fine. If JavaScript is not like the hot path in your application, you might not even notice the JIT coming into play. The interpreter is just C++ code, so I mentioned you can embed ChakraCore in your application. You can do that with just the interpreter. You don't need to bring the JIT along. And you might want to do that because the interpreter is just plain C++ code. You can compile it on any platform. So if your platform has a C++ compiler, chances are it should work on that platform. If it doesn't, file a bug. This is an interesting contrast, I guess, to V8's Ignition, which is it's also an interpreter, but their interpreter gets fed through their JIT tiers, which means that the interpreter only runs where the JIT is supported. So ChakraCore's JIT is just C++. You can compile it anywhere, and it's pretty nice, especially because it turns out that you can't always get away with JITting. So I mentioned that JITting costs memory and CPU time. There are devices out there that just don't have the amount of memory necessary to even JIT in the first place. Or maybe just the trade-off doesn't really make that much sense for those applications. IoT devices are another class of devices where usually often the interpreter is just fine. There's also software constraints, like you can't JIT in the iOS App Store. But you can actually run ChakraCore inside of iOS apps because it's just C++ and it's actually an interpreter, not a JIT. So ChakraCore has actually been deployed in applications in the iOS App Store, which I think is pretty cool. So the profiling interpreter is going to be running your code, and it's gathering profile information, and it's going to pass that profile information off to the bytecode, or the bytecode and the profiling information off to the JIT. And one of the things that we worked on recently is we isolated the JIT process from the main process. It used to be that the JIT was in a separate thread, so it was still running in the background, but it was in the same process. Now the JIT is out of process, and that has some really nice benefits in terms of security. The JIT is kind of a high-risk area because it's responsible for creating executable bits of memory. And so by pulling that out of the main process, it adds a good amount of isolation and is pretty nice for security. So we go from the interpreter to the JIT here, and so the JIT, which stands for just-in-time compiler, like I mentioned, its job is to produce machine code. And so ChakraCore's JIT is actually multi-tiered. So I mentioned like the interpreter, it spends nothing, executes code immediately, but more slowly. We also have a full JIT, which spends as much CPU and memory as it needs in order to generate the most optimal code possible. And we also have a tier in between called simple JIT, whose job is to produce code that's pretty good, but don't spend all that much time building it. It's faster than the interpreter, but it's not going to be up to the same performance level as the full JIT in many cases. This multi-tiered architecture is what enables really high throughput because it means you're always executing code, and you can sort of tune the heuristics so that these JIT tiers are coming into play at just the right time. So the simple JIT starts executing code, waiting for the full JIT to come online, and it switches over all seamlessly. So it helps push as much code as possible through this architecture. Much like everything else in ChakraCore, the JIT is fully cross-platform. So you can run it on Mac OS and Linux. It only supports the x64 architecture, so keep that in mind. But this is something that we've been working on really hard over the last year, is bringing this JIT to a bunch of different platforms. As I mentioned, it runs out of process, and it's constantly getting smarter and faster. When you hear about us runtime devs talking about new fancy optimizations that we've done, a lot of them land in the JIT. So for example, I talked about the function body deferral optimization earlier, which was like you can skip parsing a function. But we've also done work to say, oh, well, we had to parse this function up front, allocate a bunch of memory for it, all that stuff, but it seems like we're not going to call it again. So we've implemented an optimization in that case to just throw away all that memory, and if it turns out later we were wrong and we need that function, then we can bring it back, rehydrate it. But this is a great way to save memory on on a lot of top sites, actually, because it turns out you guys are shipping a lot of functions that you call only once. So after the JIT compiler does its job, it sends the machine code back to the execution engine. Now we're off running fancy machine code. This bailout edge here is just saying sometimes the JIT makes wrong assumptions about how your code works. It's JavaScript, right? You could have a loop, a million iterations, everything is a number, and then on the 1,000,001st iteration, someone calls an eval for some reason. It's JavaScript, right? That stuff happens. So in those cases, we have a bailout. Another component that I want to mention is the garbage collector. Garbage collection is really important for delivering high-performance JavaScript applications. JavaScript produces a lot of garbage. It's not your fault. It's how the language works. And so you need a really good garbage collector to keep up with that. ChakraCore's garbage collector is really quite advanced. One of the features that I think is really nice for embedders is that you can do partial time-bound collections. So if you're trying to hit a timing window in like a game, like your AI only has a certain amount of time to figure out its next move, you can tell ChakraCore, you have 10 milliseconds to collect as much garbage as possible. And it'll go off and clean up as much as it can and then be done. So that's super handy for developers, I think, especially embedders. Benchmarks are not something that we really look that hard at on our team. We are really primarily focused on real-world websites, code that we see out in production. And also, we rely on you guys to tell us what is important for you performance-wise, what your experience is, and basically what we can do to help. So I would love to talk to you about that later today. I'll be upstairs. But the general story is benchmarks, they're overall pretty good. So as I mentioned, all this ChakraCore stuff, open source and on GitHub. All of this development occurs in the open. So this is a great way to keep up with what's new. There's documentation here, including the documentation for those C APIs, those JSRT hosting APIs for hosting ChakraCore in your application. The docs are there. You can file bugs and feature requests. Binaries are there. If you just want to get a little executable that has ChakraCore in it, you can get that from there. Remember NVS, though, if you want Node ChakraCore, that's probably the right way to do that. And you can send pull requests. If compiler dev is something that you want to get into, this is open source. There's a bunch of bugs that you could look at. There's a Gitter channel you can hop in if you need help. So definitely check out the GitHub page. All right, so that's all about ChakraCore and a little bit, actually, about how ChakraCore delivers the best JavaScript experience possible. But there's actually two aspects to scalability. Well, there's probably many. But one is, like, how do you even run these massive JavaScript applications in a way that's nice for users? But the other is, how do you even develop such a massive application? How do you develop JavaScript when you need an application that's tens of thousands or even hundreds or even hundreds of thousands or even millions of lines of code? These applications exist. And also, how do you do that in an environment where you have large teams that need to collaborate on this massive code base? This is really hard with JavaScript, but TypeScript makes this easy. TypeScript is a superset of JavaScript. It's basically just JavaScript with an additional layer of static types on top. And we like to say it's JavaScript that scales. It makes development at scale just so much easier. And it does that in two primary ways. The first thing that it does is it gives you excellent tooling, pretty much regardless of editor, based on the static type information in your program. So I have a demo of that, and I'll give some more details in a second. And it also lets you use the latest JavaScript features in any browser, which is really important because you don't want to be stuck programming 1995 style to support older browsers. You really want to start using these new, handy, useful features in your development, but not have to have your clients actually use them. So that's what TypeScript enables. So TypeScript's type system prevents bugs and mistakes at compile time. So common JavaScript mistakes that JavaScript developers make are, for example, you mistype a property name. You just get undefined in JavaScript. TypeScript will tell you, yeah, you probably meant something else. If you call a function with the wrong number or type of parameters, if you try to access something that's null or undefined, like these are things that TypeScript can warn you about at compile time before you've even run your test suite, let alone discovered something horrible in production. And a lot of these issues can actually be automatically fixed. We call them quick fixes. And in a lot of cases, like in VS Code, you'll just get a light bulb. You click the light bulb, and it'll just auto-fix the problem for you. But this is the main reason why I use TypeScript. You can refactor massive applications really easily and really confidently. So for example, if you want to rename a function, and say that function is exported from a module, maybe it's used across this file in a number of different places, the typical approach in JavaScript might be to find and replace, but find and replace often leaves areas behind, gets you in kind of a weird intermediary state. It's not usually the best experience. With TypeScript, you can right-click on an identifier, hit rename, and it'll rename it across your entire application using that type information to make sure that everything is done properly. This is really, I think, the key enabler for building applications at scale in JavaScript. And TypeScript works in any editor. Since Angular 2 came out, I've heard from people saying, like, yeah, I like TypeScript, but I don't want to use Angular. We love Angular, but Angular is not the only way that you can use TypeScript. In fact, TypeScript is extremely popular in the React community. You can use TypeScript with Vue, with pretty much any library or framework that you're thinking about using. TypeScript supports it. Additionally, TypeScript supports a bunch of different editors. I happen to be biased and think that VS Code is the best experience, but I also used Vim for like 2 decades. Experience is okay there, Sublime Text as well. Most of the big editors have pretty excellent TypeScript experience. So chances are, regardless of what libraries, frameworks, editors you're using, TypeScript will just work for you. So on the other side of the equation, like how do you write modern JavaScript code, like ignoring types? How do you just write modern JavaScript code and support browsers of the past? The way TypeScript does this is by compiling your future JavaScript code plus types into past JavaScript code. So the target is configurable. If you want to support the ES3 language, that's basically IE 6-ish. You can do that, or you can target ES5, that's basically IE 9-ish. But the general idea is you can pick a target that meets the needs of the browsers and other clients that are going to actually be running your code. So TypeScript supports the stage 3 plus ECMAScript proposals. This is just spec ease for saying that features for JavaScript that are in the pipeline but that actually aren't standardized yet are included in TypeScript as long as they're stage 3 and above, which is the stage that things get pretty baked. And this is really great because, one, it allows TypeScript to be a really great producer of feedback to the standards process by using these features early. You guys even could be giving feedback to the standards process by letting the TypeScript team know what your experience is. But it's also really great because these features are awesome. They're really fun. And as a developer, using the latest language features is really a nice thing. Over the last few months, ES 2018 features have started landing in TypeScript. That's the version of JavaScript that will be standardized next year. Async generators and iterators are what you get when you combine an async function and an iterator. So it's like a generator you can await in, or an async function you can yield from. Optional catch clauses. I know half of you are now thinking, excellent, I've been waiting for ages for this, and half of you are thinking, I am really upset about this. And I understand, but it turns out that a lot of people want to not handle errors in a specific way, and tooling will warn you if you put the E there, but you don't actually handle it. You see a lot of comments for ESLint to ignore this line. The syntax just lets you leave out the E, so that's also coming to 2018 and is already implemented in TypeScript. Also dynamic import, it's kind of like a standard require. It returns you a promise for a module, and it enables you to dynamically import things, which is useful if you want to do like caching or delay loading, lazy loading, that kind of stuff, advanced module dependency scenarios. TypeScript is always getting better. If you haven't looked at TypeScript since 2.0 especially, you need to take another look. It's gotten so much better. 2.0 roughly added the nullable types, which I think changed a lot of the game. But some of the more recent things that we've been working on, the -- strict preset, this opts you into the strictest form of TypeScript. Previously, you had to select a bunch of opt-in flags to get this configuration. Now it's just strict, and it's pretty much the best TypeScript experience there is. And also check.js. Like you all have JavaScript files. You could be running TypeScript on those files and finding bugs right now. That's what check.js does. I'll show you how that works in just a second. 2.4 added stricter callback typing. The TypeScript type system is always evolving, trying to find new ways to find bugs in your program and give you, the developer, better feedback so you can build better quality software. 2.5 added some new quick fixes like JSDoc style type annotations. You can automatically convert them to TypeScript style. If you're used to JSDoc, that might happen. Also, extract function and extract method refactorings are amazing. There's something that I really missed from C#. So I have a demo here, which I'll show you some of these features in action. Okay, so I have a fairly reasonable JavaScript file here. It's just plain old JavaScript. I'm using the VS Code editor. And so the first thing that I could do with this JavaScript file is turn on that check.js mode. One of the ways that you can do that is just by adding this tscheck comment to the top of your file. This just tells the TypeScript compiler to go into this file and check it for issues. And sure enough, we found a couple issues. So we haven't annotated our program with types at all, but we still know that the platform comes with certain built-in things like object-defined property. And we know that this guy takes a descriptor. So we can check the type of the descriptor to make sure that it's correct. And in this case, we found that this read-only property doesn't exist on a descriptor. Actually, what was meant here is this should be writable true, not read-only false. So you can go in and fix that problem. All right, coming down to the next red squiggly here, it's warning us that you can't compare a function with a number. Yeah, it's right. We just forgot to call the function. JavaScript is actually really happy to compare functions and numbers. But TypeScript prefers you not to do that. Okay, so we fixed that bug, and here we've got a typo. We've just called trin instead of trim, so we just need to fix that. Note that it's lifting the type annotation from the JSDoc comment, so it's using the JSDoc comment to drive some of this tooling. So all I did was add this comment, got a bunch of red squigglies, worked through my file, fixed some actual bugs, so that's pretty nice. But we can actually go a step further if we go a little bit deeper down the TypeScript rabbit hole. So if we rename this file to .ts, now it's a TypeScript file, and now we're in that really strict pedantic mode that I mentioned earlier that really does a phenomenal job of preventing bugs. So I've removed that comment from the top. We don't need that comment anymore. This is a TypeScript file. Of course, we want to type check it. One of the things that we have to do now is move our type annotations out of comments and into the program proper. And since I don't have anything else in there, I can just go ahead and delete that. OK, so now we've got some additional red squigglies. And what's happening here is TypeScript is concerned by the fact that document.getElementById can return null. It wants us to handle that. And that's pretty reasonable. So let's go ahead and do that. Let's just pull this out into here. And then we can say, if not element, then, oops, put element back here. Then throw new error, say, invalid wait. OK, so I've done that. Now it's saying, OK, so text content might be null or undefined as well. And so we have to handle that case. So we can just go ahead and say, or not element.text content. Content. And now that red squiggly goes away. This is actually some fairly new work from the TypeScript team to make this work. You may have noticed that it's actually understanding the control flow of your application and updating the types of the variables in your program as you move through the control flow in your program. TypeScript knows that you've checked whether element is defined, so the type of it after it says, nope, this can't be null. We know this exists. This is a really powerful feature and enables some pretty awesome tooling scenarios beyond what I'm showing today. So there's also those refactorings that I mentioned. So like, let's say if we just want to pull this out into a function, it's kind of simple, but you know, pretend like we just wanted to call it something like is valid. Oops. So here's the rename symbol, is valid email. So notice it renamed it down here too and pulled it out. So extract method, like I got it working right after the team shipped it, and I've used it so many times because it's really just a really handy feature. If you have a class, you can extract it into a method of the class as well, so keep that in mind. So that's just a quick demo of how TypeScript development can really make JavaScript development a lot nicer. Much like ChakraCore, TypeScript is also open source. And a bunch of the design work that goes into TypeScript, designing these new type system features, designing these new refactorings and quick fixes and all of these new things, a bunch of that work happens in the open on GitHub. So you could track it right now. All of the design meeting notes are posted, and you can just keep on top of it and give us your feedback. We'd love to hear from you. Documentation is there, bugs and feature requests as well. And if you want to do compiler dev and C++ isn't your thing, TypeScript is written in TypeScript. So you can actually implement this compiler in the very language you're writing a compiler for. It's really fun. And it's mostly JavaScript. So if you're familiar with JavaScript and you want to get into compiler dev, TypeScript could be a really awesome project to work on. So please consider it. A little bit over time, so I just want to move through this quickly. The future is really bright, I think. There's a lot of really cool things happening. I originally had this slide just absolutely cram-packed with stuff, but I picked my 3 favorites. So first of all, ChakraCore and TypeScript are continuing to track the latest ECMAScript evolution. So the latest ECMAScript 2017 spec that's already supported in ChakraCore and TypeScript, and ES 2018, which is coming out next year. ChakraCore is working on it. TypeScript already supports much of that. WebAssembly, and especially as part of that, shared array buffers and atomics, as implemented in ChakraCore, I think have huge potential to change the way we program on the web. There's a number of ways that WebAssembly is exciting. Right now, it's in Edge, serving as a compilation target for C and C++ applications. But I hope eventually we'll evolve to support, and we're working towards supporting other languages than C and C++, even dynamic languages, even languages like C#, and having them interoperate with the rest of the web platform, be able to call into JavaScript, call JavaScript APIs, and all of that stuff. As someone who came from a Ruby background, I just can't wait until I can use Ruby on the web. And TypeScript's type system is always improving, like I mentioned. Like, you can go on GitHub and watch and be a part of building the tooling that you really want to see. So with that, I hope to see you out on GitHub, and I look forward to talking to you upstairs.
Thanks a lot, Brian.